Ja. Tak, a, wyłączę. Jest OK. Zaczynacie równo, czy? OK. Rozumiem, że 45 minut, tak? Tak.
Hello, everyone. It's my pleasure to welcome you to our next Tuesday seminar. Today's speaker is Pawel Swaczyna from the Space Research Center of the Polish Academy of Sciences. Paweł actually was a student at our university. He studied theoretical physics at the Faculty of Physics. Then he did a PhD at the Space Research Center. Then moved to Princeton, where he spent a couple of years, and now he's back in Warsaw. And today he's going to tell us about our neighborhood and the interstellar matter, observations of the interstellar matter from our solar system. The floor is yours.
Hey, thank you very much. Good afternoon, everyone. Thank you very much for inviting me to give this presentation. I'm very happy to present these results to more astronomical community. So I try to be quite simple, but I need to put what I'm doing a bit of I think in a astrophysical perspective. And first of all, I think what is very important is to remember that local interstellar medium as a term that's not very well defined, and unfortunately means different things for different people. Especially what's different is the scale of this interstellar medium, of this local interstellar medium. So some astronomers would say that local interstellar medium is something that you can see here on the left side. So basically, what we have at scale of few hundred parsecs, and basically at this scale we see relatively empty space with low density but high temperature plasma, which is called local bubble. I'm not going to talk about details, how it's created, but that's the picture on this scale of a few hundred parsecs. If we go to smaller scale, which is a bit closer to what I'm going to talk about, of just few parsecs, then we see observations, few astrophysical observations suggest, and I will talk about that later in my talk, that there are few much denser clouds than this local bubble that are around our sun. Here there's more artistic view. Not all of those stars are actual stars in this plot. But basically, we see patches of denser matter in this local bubble, in this rarefied region. Okay, but we are inside one of those clouds, and I will get to that why we think so. But before we understand how we measure the interstellar matter in the heliosphere, we need to talk about the heliosphere. So I know that that's probably not the kind of topic, so I just bring Heliosphere 101 a bit. So basically, the heliosphere is created by source of the heliosphere is our sun that emits solar wind. Solar wind is basically a plasma emitted from the solar corona with it starts with speed of around 400 up to 800 kilometers per second. That is expanding initially radially from the sun up to some distance, and I will get to this distance in a moment. On the other hand, we are of course in something that I will here call very local interstellar medium, just to be a little bit more precise compared to this local interstellar medium at different scales. This immediate interstellar medium that is around the heliosphere, I will call it very local interstellar medium. And of course, we are moving relative to it. So typically, of course, we consider the solar frame. So this interstellar medium is moving relatively to us. And of course, because these are both created with some plasma, they do not mix easily, at least not easily. And basically, the solar wind needs to expand in its own region, and its own region is called inner heliosphere. And on the other side, we have something that we call outer heliosphere. So that's the region where this interstellar medium deflects around the heliosphere. And of course, there is a question how we can measure that, how we can study the heliosphere. And of course, because we are talking about plasma, would be to measure that in situ by different spacecrafts. And in human history, basically, we have 5 opportunities. So the first spacecraft that was on orbit that is leaving the solar system is Pioneer 10. We lost contact with Pioneer 10 in early 2000s. Basically, it went up to 80 AU. Unfortunately, there's not a lot of data. This was very pioneering mission, and basically the data are sparse from this mission. Soon after, there was Pioneer 11. The contact was lost even sooner in 1995. The last data are from 43 AU. And as you can see, both those spacecraft were lost, the contact was lost when they still were in the supersonic solar wind. And you probably heard about, so next is Voyager 2. Important note, Voyager 2 was launched first, which was launched in 1977. And you probably heard that both Voyager 2 as well as Voyager 1 was launched. I hope that's all fine. Voyager 1 that was launched a little bit a few weeks later. They both left the heliosphere. So you probably heard a bit of that. You know, there are first human-made objects that left the heliosphere and entered the interstellar medium. So that's what we mean by that they are beyond the heliopause. There are a few scientists who still oppose that, who still are claiming that we are in some weird region of the heliosphere and we still haven't left. But I would say there are just few of them, and I think that more or less consensus that we are outside. And the last mission that can measure the heliosphere is New Horizons. It's still inside the supersonic solar wind. Hopefully, in a decade or so, maybe it's more, it will enter the heliosphere. This is a very interesting region, the heliosphere. So we really hope it will survive until then. So both Voyagers and New Horizons are still operating. So we are getting data from all those three spacecraft. However, as you can see, that's tough. That we have only basically 3-point measurements of heliosphere. That's really hard to say something about such a huge structure. So there is other way, and the obvious way, so while plasma is to separate, neutral atoms can transverse all these different boundaries and can go around the heliosphere. And of course, we have interstellar neutral atoms. There are, of course, there is gravitational deflection. I will get to that later. But also other atoms can travel through the heliosphere. And basically, we have two, or currently we have one mission that is on Earth's orbit, Interstellar Boundary Explorer, that is first dedicated mission for observation of heliospheric energetic neutral atoms. Energetic neutral atoms originally were discovered as coming from the Earth's magnetosphere, But it was soon realized that actually these energetic neutral atoms, and I will get to this energetic neutral atoms in a second, can be used to actually observe the heliosphere. And soon, in about a little over a year, probably in early 2025, there will be launch of new mission, Interstellar Mapping and Acceleration probe, that will be much better version of IBEX, basically. And what is the idea for observation of this energetic neutral atoms? Basically, the charge exchange. So while in the plasma, of course, they follow the plasma flow, the process in the plasma follow plasma flows. When they are neutralized, they will follow basically ballistic trajectory. So they are connected to a plasma, for example, in the heliosphere. But after neutralization, they can get, from distant region, for example, from heliosphere to 1 AU. And that's the main idea in something that some people call neutral atom astronomy. I would say that this is a bit overstatement, but this is the way some people call it. Okay, so what are the sources of these neutral atoms in the heliosphere? So the first source that we can, let's have our IBEX IMAP somewhere. It's probably not scale in terms of distance from the sun. So first of all, we can have something that we call primary interstellar. And these primary interstellar neutral atoms are something that some atoms that originate from this very local interstellar medium and get directly to our detector. The second source is something that we call secondary interstellar neutral atoms, which are created from interstellar ion that is already within this plasma in the outer heliosphere. So it was somehow processed, was somehow deflected. This plasma was deflected, but it was charge exchanged mostly with the primary interstellar atoms and became neutral atom that can be measured by IBEX. The third source that we originally was thought that this would be most important source of energetic neutral atom is the following. So basically we have so we have primary interstellar neutral atoms. There's red points showing you where it's ionized, mostly through charge exchange with solar wind plasma, but it also can be photoionization, electron impact ionization. It moves away with the solar wind, so that's why it's called pickup ion. Before it's sometimes interstellar pickup ion. At the termination shock, there is typical process of energization of those ions. And in the heliosphere, there is another charge exchange. It's unfortunately behind this bar, where it's neutralized and creates energetic neutral atoms that we can detect with IBEX. And after the launch of the mission, it was realized that there is actually the fourth source of neutral atoms that is important, that can be seen with IBEX, which is the secondary ENA mechanism. So I said ENA means energetic neutral atoms. In this source, that's even more complicated. So we have neutral solar wind. We have solar wind ion, which is neutralized, exit the heliosphere as neutral atom. It's charge exchange twice. So first it's becoming pickup ion, then it's neutralized again, and it's detected as neutral atom. So you can see this is quite complex process. And it was originally thought it won't be strong enough to be observed, but actually in observation it is observed. I'm not going to talk about that, but it turns out to be quite important source. Okay, so this is the summary of this four most important sources of neutral atoms. I'm going to talk here mostly about this primary and secondary interstellar neutral atoms, and also about pickup ion, because that's where my main interest is. Okay, so a bit about Interstellar Boundary Explorer. That's a relatively small mission. The mission's PI always compared IBEX to a bus tire. So it's about 80 centimeters, diameter of 80 centimeters. It was placed on orbit around Earth. And from this orbit, it's constructed so that the two detectors are pointing in opposite directions, but are also pointing perpendicular to the sun. So basically, it's a rotating spacecraft, and it's always so rotating that the spin axis is close to the sun. Of course, it's repointed every few days, more or less between 3.5 and 6.5. Early in the mission, it was days. Early in the mission, it was more 6.5. Now it's more 3.5. And based on that, we have this spin axis, and the field of view of those two detectors. These are basically single pixel camera. So we basically see we only see that this is more or less from one of those two directions in which we are pointing, that we are seeing some atoms. And basically we are scanning around great circle, and basically you can see that from this scanning around great circle, we can throughout the year do a map of this ENA emission. So that's we need entire year, or at least half a year, but in practice we need a year of observations to make a map. These two instruments are not identical. These are two different instruments. One is dedicated for low energy atoms, such as interstellar neutral atoms. They're moving with speeds of order of 20, 30, 50 kilometers per second, close to Earth. And high energy, which are measuring atoms of speeds of few hundred to few thousand kilometers per second. The difference is in how these detectors change neutral atoms into ions, because the idea is, so first of all, if you want to observe neutral atoms, you need to remove charged particles. You don't want to observe charged particles and you have a lot of charged particles around you. So you need to remove them, and there is some bias potential at the entrance to basically avoid new charged particles getting into the instrument. Later, you would like to know something about the energy of this atom. And that's not very simple, especially for low energy atoms. There is no good way to detect energy of low energy atoms. So the way it's done is actually to charge it somehow. And after it's charged, you measure energy of charged particle. And in case of IBEX, this is done through sputtering through ionization and the conversion surface. And in this case, we are getting mostly negative ions. And for IBEX high, it's charging at the conversion foil. So this is very thin carbon foil, and some particles going through this thin carbon foil will be charged actually positively. So they are actually measuring, low is measuring negative and high is measuring positive ions. And eventually there is a basically detector of ions inside. Oh, I forgot. The most important thing is to measure energy. It's used electrostatic analyzer. So basically there is this this U-shaped region where basically only atoms at some energy that is set based on the voltage on these surfaces will go through the instrument. Basically, the other are lost. So we can select the range of energy for a given time that we are observing. Okay, so let's go to neutral atoms. So neutral atoms are relatively, so we are moving relative to our interstellar medium with speed of about 25 kilometers per second. Of course, these atoms are accelerated by solar gravity. So at around Earth, they have speeds of, let's say, about 50 kilometers per second. And of course, the question is, it's very important because Earth is moving also with this 30 kilometers per second. It's very important whether we are moving against the flow of this particle or with the flow of this particle. So only on the part where we are going against the flow of the interstellar particle, we actually have enough energy to detect them. So even though you would expect to observe them on two sides of the sun, because in theory that's symmetric, in practice we observe them only on one side of the sun, because on the other side the energy is not large enough the atoms don't have enough energy to be detected. So in practice, what we see, this is one of those maps that you can make. This is showing 3 different energy steps. So the highest plot here is showing actually a mixture of hydrogen and helium atoms. The second plot is mostly showing helium atoms, and this bottom one is showing the heaviest species that we observe. So mostly it's oxygen and neon. So that's more or less what we can observe with from the interstellar medium around us. Okay, I talk about that just a quick reminder. So we have these 2 populations of interstellar particles. So we have primary coming from the very far interstellar medium, and something that was created in the outer heliosphere, which is called the secondary atoms. And because they are created in this region that was already slowed down because of the heliosphere, they will be slower, but also will be a little bit warmer. And because of that, we observe them as follows. So basically, we see this picture, and it's showing how we point our instrument in the sky. So it's not accounting. So in making this video, we are not accounting for the gravity. So that's why we see that this peak of the primary, in this case, it is mostly helium. We are focusing on helium because of gravitational deflection. For hydrogen, the situation is different. I'm not going to talk more about hydrogen for 2 reasons. First, it's observed only the statistics is much lower, and because hydrogen is much more effectively ionized closer to the sun. So we don't have close to the sun as much hydrogen as we have helium. And the second reason is hydrogen is significantly more processed, so it's not as good to say something about the interstellar medium around us. So it's more, we are focusing on helium. Still, we see both populations. The secondary population, as you can see, is showing larger part of the sky, and you can imagine that that's basically that you are looking at the velocity distribution function in some way. That's of course very simplified, but you are looking at the velocity distribution function. So if the signal is broader, that means that it's basically hotter, and it's because it's more deflected because it's slower. So these are these important factors here that are, for example, used in one of the way of analyzing that. Basically, the way it's looking where this peak is of the signal, and now knowing that it was deflected by gravity, you can derive the relation between the speed at infinity and the deflection. And this creates something that we call correlation cube, because there is basically a set or range of possible combinations of speed and direction in the space that corresponds to the same peak position. It could be this correlation could be broken by something that's called here the second step, which is basically if you look into how different parts of the distribution are deflected. This flow, interestingly, is actually, I haven't said that, but it's very important. This flow is very close to the ecliptic plane. So it's just 5 degrees away from the ecliptic plane. For the purpose of that, that's for the purpose of this first step, that's very small. For the purpose of the second step, actually this reflection is used to break this correlation. And the final step is actually getting temperature. And that's one way of analyzing that. Of course, there is other way, which of course will get to the same correlations in the end. It's basically doing forward simulations and comparing for different parameters that we assume for the interstellar medium and compare that with our observation. And that's a much better way, because we can account for the secondary population in much better way. And the reason why we need to account for this population much better is because it's significantly processed. And so I already said about charge exchange coefficient, so that's basically how we are getting the secondary population. But on top of that, there are elastic collisions. And that was for a long time, it was not considered because it was thought that these collisions are not important. So basically, one can ignore those elastic collisions. So I took this topic a few years ago. And it turns out that that's not true. These elastic collisions are strong enough to change this problem. Fortunately, it turned out that typically elastic collisions for not as low, but for the collision speed of the order of a few kilometers per second, 10, 15 kilometers per second, typically the most probable scattering angle is close to zero. So here are the cross sections for differential cross sections. And you can see that very low scattering angles are much more probable. And here is just example of 10 simulated, maybe more than 10, a dozen or so of simulated trajectories with the dots representing basically the scattering. And these scatterings are occurring, at relatively large distances of at least of the order of 50-100 AU, but still, as they go through the outer helioship, they modify the population. And typically in the outer helioship, we have about each atom that is going through the outer helioship collides up, which means that it's definitely not something that can be neglected, at least not completely. Fortunately, the trajectories are not modified significantly. So, of course, as you are in the very localized star medium, then those elastic collisions, they are basically thermalize the population. But if you are in the region where there is separation of the atoms and plasma, then it's what's happening is only modifying slightly the population of the neutral atom. So it's not completely, it's not strong enough to thermalize them because of the small scattering angles and because we have just a few collisions, but it's strong enough to make some modification to the distribution function. And here's a result of what we are getting going through the outer helioship. This top row is showing with accounting for those elastic collisions, or here it's called also with angular scattering, because on top of that, it's accounting also for charge exchange and angular scattering in there. It's getting this tail of at low speed relative to the sun. This is actually centered at zero. So it's if you look in the solar frame, the zero is actually somewhere here, and it's also a slightly broader distribution, which means it's this population is warmer. And if you look into the simulations, what it does for the signal, so these two top in the middle panel are showing with and case with and without scattering, basically the model result of modeling, and the bottom one is showing the difference. So there is some significant difference, and on the right, it's showing how all these different populations, so primary and secondary, how they change compared to their pristine interstellar medium. And, of course, now there is a question, what is impact of different interstellar conditions on that? So what we can actually learn from observing this interstellar helium about our interstellar medium, and here it was what I tried to do is to check how different parameters that describe the interstellar medium change the signal. So, for example, we have changing speed, changing temperature, changing magnetic field strength, and so on and so on. Of course, here you would say, oh, that's probably just 11 of the same plots. So, of course, it's more important to look in difference with a baseline model, and then you can see what different parameters do to this signal. And for example, one reason you should compare that with this case here in the last column and middle row, that is showing case with and without accounting for this elastic collision. I selected the changes of various parameters based on our knowledge or estimation of those parameters from other studies. And you can see basically that each parameter changes this view slightly differently. So it is possible to try to find actually the simulations, the set of parameters that will give you the best fit to your actual observation from IBEX. And here is the results. I just want to point out here that, for example, for the relative speed to the interstellar medium, this accounting for these elastic collisions is modifying the speed. So we are actually moving with slightly higher speed, 26.6 instead of 26.2 that we thought previously before we actually started accounting for those different scattering effects. Okay, so sorry, and also similarly for temperature. So the actual temperature is lower than we thought. So previously we thought this was, or would thought that this was about 8,000 kelvins, and it's why it's actually closer to 7,300. Okay, so these are the parameters that we know from our interstellar observation of interstellar helium, which is, as you can see, most important for us moving on are these first four. So basically speed, the flow direction, and temperature. And why that's important? Because we can relate that to other astrophysical observations. And that's probably very simple for you. We can say something about this in the clouds that I was talking about at the beginning, based on absorption in the slides from spectra of distant stars. We can see absorption from those clouds, and we can basically, based on that, say what is the radial speed of this cloud relative to the sun, and based on that, we can say about the structure. And that's something that was done already first with ground telescopes. Here there is results from Lamont and Bertin paper from 1992, where there was discovery of two clouds, which was originally called galactic and anti-galactic clouds, that were observed, and none of these clouds was observed in all directions. So basically, there was idea looking for one velocity vector that would match, matching projections to different directions to different stars, that there would be one cloud that would, surround the sun that would be observed in all directions. That was not the case. There was no cloud that would match with just one single velocity vector, just projected at different radial directions. So they concluded that there are probably two, they call it galactic and anti-galactic cloud. And soon after that, this anti-galactic cloud was found that the velocity was consistent with very, very early observations from other missions, not IBEX, but previous mission that observed interstellar medium, interstellar helium on Ulysses. On Ulysses mission, that was instrument gas on Ulysses. It measured, and this was appeared to be consistent with anti-galactic cloud. So this anti-galactic cloud was soon after renamed as local interstellar cloud, and the conclusion was we are inside local interstellar cloud. However, with Hubble Space Telescope, it was possible to make much better observations, because a lot of these absorption lines are in the UV spectrum. So there is a series of papers by Reggie Deminsky who looked very carefully into that, and what they concluded with is basically this model of complex of local interstellar clouds. Then you saw this I would say more artistic view of this figure previously at the very beginning of my talk. Basically, they concluded there are few different clouds around us. each with slightly different velocity vector that could be identified from those observations of absorption lines. And these two closest to us, so LIG, previously known as anti-galactic cloud, or galactic cloud, which is often shortened as G. The velocity vectors are here, and you can see already that there is a problem. And I will get to that in a second. But it's important that LIG and G are observed in two separate directions in this part of the sky. So this is plot centered at the galactic center, and showing in which direction we see absorption from LIG, and in which direction we see absorption from G cloud, except with very few small patches where we see absorption from both clouds. Unfortunately, that is also where where the difference in radial projections is very small. We see them in different parts of the sky. And here we are getting back to where there is a problem. So basically, when we compare the speed of LIG and G cloud, and we compare with the current, our estimate of the local flow near the heliosphere, they are not consistent. Our flow near the sun is not consistent either with LIG or G cloud. The speed is it seems to be different, and it's very statistically significant. So much that if we took into account all the turbulent flows that repeatedly predicted for the LIG cloud, it does not explain, or the probability that this is just a random turbulent move inside LIG in this case is extremely low. So I ask the question, okay, so maybe we are in a region where we have influence of both clouds, and we have some kind of mixing of those two clouds, and of course that's the actual fact. It may be very complicated, but the question was, okay, is it possible that we are in a region where we have some part of material from one cloud and some from the other, and we can basically estimate what would be the velocity of this mixture and compare that with its velocity? And it turns out we are in almost 50-50, or accounting for uncertainties, we are in a 50-50 mixture of these two clouds. So our flow is consistent with basically linear combination with almost equal weights of those two clouds. Okay, so that's interesting, but do you have any other argument that there is this mixing region? And that was figure that I saw when I was I at first saw when I was seeing that this discrepancy, and I realized this was a paper by Jedlinski from 2022 that it's showing. Please focus on the right hand scale. So on this inset scale here, it's showing the average density of hydrogen to different stars, close stars up to 10 parsecs. Compared with distance to the star. And you can see that there is one outlier, and this is 8 ionized. And it turns out there is only one other outlier that is showing density, average density. Of course, we can get only column density, but average density to the star that is also very high, which is HD 82558. And there are two very significant outliers are showing both about 0.2, and all other stars are showing actually below 0.13, or the column density to the stars. And what Jedlinski proposed in the paper, okay, so there is one more important thing. So you can see this red crosses, which are showing stars that are inside the LIG. So they are showing only absorption from the LIG. So if we are in the LIG and those stars are in the LIG, this would suggest that this should be the typical density of the LIG. Or there is something that he called Swiss cheese model. So basically, that there are holes inside the LIG. Or LIG, I'm using the LIG acronym, which is basically local clouds. that either this link is of just the density is 0.1, or there are holes inside the link. And we also know that our density close to the sun, and I will get to that in a second, is also higher of the order of 0.2 or 0.20 to 0.19 per cubic centimeter. So maybe we actually are, so this is very simplified model of this interaction, which is basically just two spheres or two balls that are that there is some overlap between those two balls where there is this mixing region, and we are inside this mixing region. But interestingly, it turns out that if we look in the different directions and see where there is a significant portion of this mixing cloud in the sky, that's basically forming a ring of increased of where we are passing, or line of sight are passing through a significant portion of this mixing region. And these two stars that I was talking about are actually around those line of sights. So this was another suggestion that we are actually inside one of those mixing regions. Okay, and I just want to very briefly talk about pickup ions, because that's important for this hydrogen density that I showed in the second, just before. Okay, so what are these pickup ions? So I said that these are these neutral atoms that get inside the heliosphere, are charge exchanged, and are picked up by the solar wind and expand with the solar wind. So what is going on? So they first in the solar, so of course in the solar wind frame, in the solar frame, they are moving with relatively small velocities. I said this is of the order of 20, 30, maybe 50 kilometers per second close to the sun. For helium, for hydrogen is actually not so much different. And that so it's much slower than the solar wind. So in the solar wind, they are actually moving with the opposite speed to the solar wind in the solar wind frame, with high speed. So they are picked up at a relatively high velocity. They are creating something that we call suprathermal population of particles. Originally, they start to gyrate about local magnetic field direction. There is a lot of turbulence. So they are very quickly scattered probably to this shell distribution, basically. So this it created the shell distribution, but as the solar wind moves away to the termination shock, it's cooled and basically creates something that is called field shell distribution. And as you can see, this is a plot showing all these different layers. So these layers in this distribution are showing particles created at different distances. And that's a result in the spacecraft frame as New Horizons. They create those layers of different particles that are going up to about 4 times solar wind speed. So solar wind energy, not speed. Twice the solar wind speed, 4 times solar wind energy. And this is actually the real life observation from New Horizons. So here you can see this blue line is showing this population of pickup ions. I don't want to go into details. Unfortunately, we see all these other populations as well together, so we do not have a very good way to separate them, unfortunately, from this instrument. But basically, we can analyze how many of these pickup ions we have. And we did so as well in 2020. At this time, at that time, we had observations up to 38 AU. And it turned out that this density, compared to previous observations that were made also with pickup ions, but on Ulysses, it was just few AU from the sun. It turns out it was much higher. This is showing the column density from the sun to the point of observation. So all these color dots are showing observations from one single day. There is a lot of scatter, and we expect it because of a lot of processes going on in the solar wind. But on average, over each 1 AU, it's showing much closer to one line, and basically it's increasing because, except very close to the sun, where we have this cavity. So as I said, we have this region where we don't have much interstellar hydrogen. then later on they basically follow the increase more or less linearly, at least within the heliosphere. Here is just update. This is very preliminary. Still, I'm still working on that. Update with new data up to 52 AU. That is showing still that we are still having higher density than we previously thought from IBEX. So this is 0.09 old consensus. Unfortunately, what we see here and what is interstellar medium in case of hydrogen, that's very complicated story, and this results from 4 models. 3 of them that are very complicated models of the heliosphere from different groups that basically show the same density close to the sun, but far away from the sun are showing much or slightly different density. So anyway, this density that we observe at 30 AU of 0.108 is translated to more like 0.1718 per cubic centimeter. Of course, there is a lot of uncertainty just from modeling. So these three lines are showing different models, and this is very simple model. Okay, and this is my almost final slide. So what's in the future? I already said about interstellar mapping and acceleration probe. This is a mission we are waiting for. We will be able to observe interstellar neutralities not only at 90 degrees away from the sun pointing spin axis. We will have more flexibility, unfortunately, on that. We will have much better instrument with more with higher sensitivity, basically. But also something that I'm looking forward is interstellar probe. So next mission that would leave the solar system that's currently under decadal survey in the US. If the decadal survey decides to go with this mission, this will be a very interesting mission. You may not know that Voyagers were not intended as heliophysics missions. They were intended as missions to giant planets. New Horizons was a mission to Pluto. This would be the first mission actually dedicated for to observation on the stellar space, but it would still take about few decades to get to the interstellar medium. And the mission is planned for about 50 years at least. Hopefully it would survive longer. That's possible. We know with Voyager it is possible to build a mission that will last for 50 years. But it's very interesting how to make it happen, because probably not people who will build this mission won't be analyzing data. There will be new generations needed to analyze the data. So I'm very hopeful that this mission will be safe, because this would be very interesting. In first actual observations in situ of interstellar medium, except for few observations from Voyagers. We are very limited on our knowledge from Voyagers, but that's mostly because these were not missions intended for observations of interstellar medium. Okay, and that's just my summary slide. I already went over my time, so I will leave it here. Most important, I think from that is that we have ways to measure interstellar us. And what is more important is that we are not in some random space that is not interesting, that is with some mixed region without structure. We are inside very interesting region, a changing region, and we can do that to measure that with in some observations from space missions, but also with telescopes. And there is a very good synergy between telescopic observations, such as from Hubble Space Telescope, and observations from in situ observations on different spaces. Okay, thank you.
Thank you. Questions? Do we have questions?
Yeah, I have a question. What determines the direction which the spacecraft are sent? I believe that some of the past ones, as you said, they were intended to study planets, so that was probably the case. But the future ones, and also.
So that's a very good question. Actually, so of course, I'm not sure about pioneers, so I don't know exactly. I believe they were also intended for some observations of outer planets. Voyager is the same, and New Horizons is Pluto. In terms of interstellar probe, there was basically a study of possible targets, and we still target to go near Jupiter for gravity assist purposes. So we still plan to go near Jupiter, and that limits us where we can go in the sky, depending on the year and so on. So, for example, this study that was done was funded by NASA. They analyzed for more than a decade, starting from early 2030s up to 2040s, where we can go in different years. And now, I would say most interesting is going somewhere where we can exit the heliosphere relatively soon. Heliosphere is not the same in all directions, so we have tail in the opposite to the inflow. So if we go to the tail, we would stay for the entire mission in the heliosphere. But we actually want to go outside, then we need to go forward. So this limits us. And also what is limiting us typically is if we go away from elliptic, the final speed that we can achieve is lower. So we typically want to go in ecliptic. So this limit. Still, there is a few options for interstellar probe that are considered, depending basically on when they are able to launch.
The questions?
Excuse me, sometimes we are talking about ballerina scale about solar wind, and you hear that this is radial. And what is, let's say, how precise is the approximation of the radial, and how precise is the ballerina scale?
So the ballerina scale is from something different. It's from so through the solar cycle, the structure of the solar wind changes, and basically depending on the part of the cycle, so there are patches of high speed and low speed solar wind, and as the sun rotates, it may create those. It may create this, but the ballerina sphere is not as much about the direction of the flow. It's more about something that is called yeah, I forgot just now. And anyway, there is a region where the charges are going through the heliosphere, where the how the cosmic ray propagates. That's more important for.
Is it some kind of magnetic field or wind, or this is not important?
I don't think so. Well, yeah. That's a bit beyond what I'm doing, but yeah, I don't think so. It's much about so, yeah.
One here you put the density of the helium ions in the space around us. This is helium ions 1 plus, and we can let's say somehow estimate the neutral helium from this.
Oh yeah, yes. So in the interstellar, I think you are referring to the interstellar medium. So in the interstellar medium, depending on how high the helium plus density is, there is almost no alpha particles in the interstellar medium, or that's much lower than helium plus. So depending how much helium plus ions we have, it changes how much of the secondary population we have. So how strong is the filtration? So that's what we can. That's how we can actually obtain the helium plus density, and that's even more precisely than helium neutral helium density. Unfortunately, with all instruments, it's very complicated to have a absolute calibration. So in theory, you can get absolute density of helium from having a good measurements here, but unfortunately, without good absolute calibration, this calibration is good at best to 30–50%. We can say about, but because the secondary population is ratio between the what's governing this helium plus. This governs the ratio between primary and secondary population, and that is something that we can say much more precisely. That's why we can find the helium plus density much more precisely than the helium neutral index.
So neutral helium is more abundant, or
it is more abundant. Yes, it's definitely much more abundant. It's well, maybe not much, right? It's here it was. Excuse me. That was 0.009 per cubic centimeter. For neutral helium, it's 0.015 per cubic centimeter. Unfortunately, we know that similarly as I was showing about hydrogen and horizons, we know that from pickup ion observations on Ulysses. Unfortunately, it's very hard to do it on New Horizons because despite we are not going to high enough energy to do it. The instruments do not measure as well ions, but we will have on IMAP, we will be able to probably measure that much better, I hope. I mean, we will be measuring helium pickup ions very close to the sun, and we still can do that because helium is not as much ionized at 1 AU. We still have plenty of helium, of interstellar helium here. So.
I have a question about IMAP. Is the Space Research Center involved in building instruments on the satellites?
Yes. We are involved in a couple of ways. So one most important contribution from the Space Research Center is instrument is called GLOWS. This instrument will measure Lyman alpha helioglow. So basically, the Lyman alpha light that is emitted from the sun and is backscattered from hydrogen in the heliosphere. So this instrument is prepared at Space Research Center, but we are also involved in other instruments. So that's a relatively large mission compared to IBEX, but there are only 2 instruments. Here there is many more. I was talking about, for example, I'm personally involved in SWAPI instrument, which will be very similar to this instrument that is on New Horizons, from which we have information about hydrogen density. So that's why I'm very hopeful we'll have much better helium density estimation from IMAP. And also we are involved in, not only myself, but other people from the institution are involved in IMAP law, which will be detecting neutral atoms. I would say that's our main expertise in Space Research Center, these neutral atoms and the dynamic and all these changes that are going through what's happening in the heliosphere. So we are involved in all of that. Oh, and I should mention that it's a GLOWS instrument that's lead by the leader of the instrument. It's Maciej Dowski from Space Research Center, but so actually I'm not as much involved in GLOWS specifically because when it was developed, I was away. So I'm more involved with those instruments that are prepared outside for.
Okay, do we have another question? Now let's thank our speaker again.
Thank you.
Jeszcze mam pytanie o slajd numer 32. Chciałem...
Tak? Jasne.